Right, good morning, everybody. Can you hear me? My name is BRK1001, and this is Chris Edmonds, and we are so excited to be here at Build talking again about Kinect. So for our talk today, we're going to start off by I'm going to give you guys a brief overview of what the product is, the hardware, the SDKs, as well as give you some ideas of the use cases for this product. And then Chris is going to walk you guys through how to actually build your first app, starting with a Kinect for Windows app and going all the way through how to connect it to Azure. So we started this journey of Kinect about 10 years ago. And, it was this wonderful gaming accessory, came with Xbox, and we have since been completely blown away by all of the amazing use cases that you, our developers, have figured out how to make with this device. And so when we started talking about what we were going to do with the next version of Kinect, we wanted to make sure that it did a few different things. One, we wanted to make sure that it was open source SDK so that you had the freedom to contribute, to add new features, and to develop on this product how you want to develop on it. We also wanted to be able to enable different camera modes. So with this product, you can do like a wide field of view and a narrow field of view, different frame rates, and basically have that customization in both the RGB and depth cameras to, again, build the solutions you want to build. And we also wanted to include multiple mounting options, because we know you guys aren't just taking this and putting it on your table and leaving it there. You're putting it in all sorts of different places in a room, on moving robotic arms, and being able to quickly and easily do that was very important. And last, we wanted you to be able to make the most out of all of our cognitive services to be able to build your AI solutions quickly. So while this device doesn't actually require you to connect to Azure to use it, when you do apply your Azure cognitive services, you can make applications that are really amazing. So let's talk about the hardware for a minute. So you can think of this device as kind of a Swiss Army knife of awesome developer tools that you would need to build computer vision and speech models. To start off, we took our 1 megapixel depth camera that we have been redesigning and updating for HoloLens 2 and put it directly into this device. Then we added a 7 microphone array that enables far-field speech and sound capture capabilities. We added a 4K RGB camera, which is time synchronized with the depth images so that you not only know where objects or people are in the space that you're looking at, you also can get information about what that object is or more details about what that person is doing. We added an IMU. Like I said, we want you guys to be able to mount this in all sorts of different ways, and you need to be able to know how that device is configured so that you know how to read in the images that you have. With the IMU, you can do that automatically. And last, we spent time listening to our community and really understanding how you guys were using this device. And one of the things we heard was 1 camera cool, multiple cameras amazing. And so we added in what we're calling external synchronization pins. And what these are is it basically enables you to set up 1 camera as a leader and the rest follow in timing so that you know exactly when 1 camera was triggered relative to another. And you can take all of that awesome point cloud data back and stitch it together. So then instead of having a camera visioning our platform up here, we could actually have multiple cameras creating a full 3D picture of this conference room today. Okay, so let's talk about SDKs for a minute. There are 2 SDKs that are new with this product, our sensor SDK and our body tracking SDK. Both of these have been completely redone from the ground up. Unfortunately, that does mean that we're breaking backwards compatibility with the Kinect for Windows applications, but we thought this was important because we wanted to, 1, make sure that the sensor SDK was open sourced and available on GitHub. 2, we wanted to get rid of drivers. And 3, we wanted to enable you to be able to plug in multiple cameras on a single computer. For the body tracking, we wanted to be able to provide higher accuracy models, improve how many joints you're getting with the body tracking, and enable you to track more than 1 person at a time. Both of these are available on Windows and Linux. The sensor SDK is written in C, but we will also have a C# wrapper available after launch. And the last thing I want to tell you guys about the SDKs is with the sensor SDK, we are also including what we're calling the Azure Kinect viewer. This tool, which is shown in the bottom right of the screen, enables you to plug in the camera, start it up, and immediately see the IR images, the depth map, the color image, get the IMU streams in the microarray, and just see how sensitive everything is, what it looks like in your environment. As well as on the left there, you can start playing with the different modes of the cameras, aspect ratios, frame rates that I mentioned. So basically, you can set up the camera, configure it to do everything you want to do, all without writing any code. Which we're hoping helps you guys get started much quicker in building these applications and exploring what's possible. So for today's talk, we're going to primarily be focused on the sensor SDK and how you tie that to our Azure Vision services. If you're interested in learning more about our body tracking SDK, please come check us out on the expo floor where we have that up and running and you can see it working in real time. Okay, so we've talked about hardware, we've talked about software. What can we do with this device? This is not an Xbox peripheral anymore. We are targeting this product more for industry applications. And so if you think of something like manufacturing, where you have this dynamic environment of forklifts and people and conveyor belts and everything moving around, being able to get a full 3D capture of what that space is so that you know if something shifts and a pallet is placed somewhere else that day, and now all of a sudden all of your people traffic is being diverted in a different way, you can know about that and see how the flow of your factory is changing. Or, for example, when I was in undergrad, I worked at Anheuser-Busch, and for a week they had me be on the factory line, just so that I would get an experience of what that was like in order to help with the solution I was building. And while I was doing that job, it was a lot of bending over and moving around, and I was terrible at it. I was sore after my week of working there. I had no idea what I was doing. I was incredibly inefficient. If I would have had something like Azure Kinect, I could have had it watch what I was doing, understand the movements that I was making, and then make suggestions on, hey, don't put all of your stuff over here, bring it up higher so that you don't have to bend over all of the time, or relay out the station so that it's easier for you to move about. And if you imagine that's just one station, if you did that on your entire factory line, you could improve your efficiency and improve the comfort of your workers. Healthcare also continues to be a very important industry application for Kinect. We've all know and love the fitness apps and the dance apps that came before, but we're now looking into new things like rehabilitation, where someone gets injured and you have to do all of these exercises and it's tiring. Week after week, you're doing the exercise, you're not seeing any improvement. It's difficult for the physician to really measure or tell you that it's getting better. But with something like Azure Kinect and our body tracking, you can actually show how far the range of motion is improving in the customer or the patient as time goes on. Retail. So retail is kind of a newer environment space for us, but every day I keep hearing of more and more applications of things to do in retail. Some of my favorite are actually just simple knowing stock inventory management. How deep are your shelves? Is there something hiding in the back there? What are the objects on your shelves? How are people moving about in the space? And again, optimizing the layout of being able to get your customers where they need to go. And that's all just on the front end. If you look at the back end of a store where you're taking in inventory and managing, giant pallets of devices coming in, being able to scan them in 3 dimensions and know where you have space in your warehouse to put them, being able to automatically read the labels using our cognitive vision services or our OCR and know exactly what that product is, and it pops up into your inventory management live so that your salesperson on the floor knows, hey, cool, we just got a whole new shipment in of Azure Kinects. I can definitely go get you 10 of those from the back. And then the last, we can't talk about Kinect without talking about robotics. People are finding all sorts of interesting ways to, like I said, take the camera, put it on a robotic arm. As it's moving around, the robot can adjust its path to know exactly where the object is and pick it up, and to be able to detect the right object and make sure it's grabbing the right part that goes into the job. It's also being used for things like navigation, so being able to map the space and automatically find its way through the path so that, again, that pallet that I moved earlier in my warehouse that is now blocking the way, I don't need to worry about the robot being stuck. It can detect that pallet is there and figure out how to navigate around it. So those are a few examples, and while it's great for me to stand up here and talk to you guys about all of the things we're ideating about. It's even better if you can hear it from our customers themselves.
In China, manufacturing industry has 400 million industry workers, but only 5% of them are technology enabled.
Our mission is to enable those first-line workers to become experts using our technology and products.
Ava Retail is a leading provider of autonomous store technology. Azure Kinect provides you those two main components, the audio that's happening in the space, as well as the video. And that accuracy of depth sensor has been one of the best. Also because the FO is bigger, you can cover more area with a smaller device.
We've used probably every depth camera that's been built in the world. There's no other camera that could do what we needed. We're the only computer vision-based fall prevention solution in the market. And backed by Azure, we can develop services that run both in the cloud and run on the edge, the same code base. There's no other cloud provider that can do that.
Microsoft is building an ecosystem, and we are seeing there's a great potential in training, in quality checking, and also how we can detect an object for mixed reality.
This camera is a game changer in every way. I think if you step back, you think emotionally about what you can do, you will come up with amazing things that people have never thought of to do, and you can do it with Azure Kinect.
So I think Steve said it great there at the end. You know, if everybody in this room sat down for 15 minutes and thought about something that they could do with this camera, I bet we would have hundreds of new examples of things that we can do, and we just cannot wait to see everything that you guys create. But in order for you to do that, you need to know how to build your app. So I'm going to hand it over to Chris, who's going to teach you guys how.
All right, thank you, Erica. So let's get started building an app together. Here's a picture of an application from our Connect for Windows v2 SDK. This was circa 2014. And you can see here that it's segmenting me out from the background of the color imagery and then superimposing me on top of this desert scene. So we're going to take this app, we're going to put Azure Connect into it, and then we'll show you how we can connect that up with Azure. So let's take a look at this application for a second. I've updated the visuals a little bit and changed some of the styling, but overall it's the same WPF structure. So if you look here, we have two primary pieces to this application that we're going to be concerned about today. First is this main window area where we're showing the imagery here of a flower. This is our writable bitmap. This is where we're going to be writing out our pixels as we walk through this. And then there's a status text section here down in the bottom. And when you see status text in the code, this is what we're updating. We'll put information there about what we're capturing and any errors that we encounter along the way. As we get into this application, it's important to note that I'm showing you a preview of our C# wrapper for the C SDK. So some names may change a little bit as we get closer to release, but for the most part, you should expect this to be what it feels like. All right, so in order to build an application that does a similar process to what that K4W application did, here's a rough application architecture. First, we need to open the device. We need to find a camera, and we need to get a handle to it. Second, we need to acquire captures off of the camera. We then, in order to perform the segmentation step, need to take our depth imagery and convert it into the perspective of our color camera so that we can segment out the color image. That segmentation step is in part of our app-specific logic, along with drawing those pixels out to the screen. And then we just loop that over and over again for every image that we receive in. So the orange boxes here represent the things that the SDK helps you out with. And then the green boxes are our application-specific logic in this case. All right, so we're going to start off with opening the device. So here's some code on a slide, which you'll be able to access later. But it's better if I can show you code in Visual Studio actually working. All right, so here we have that WPF application. You can see my main window class here. And then I've added a field to this class called the Azure Connect device. And I've named it Connect and set it to null. In the constructor for my main window, I say Azure Connect device open. And I haven't provided any parameters. So when I don't provide any parameters, that says open the default camera, open the default device. I could also optionally specify an index of a camera based on having previously queried for serial numbers of the cameras attached to the machine. Another exciting thing about our SDK, the Azure Kinect SDK, is it actually supports multiple cameras on the same machine, where Kinect for Windows only supported one, and you can even have multiple cameras in the same application. We then, once we've opened our device successfully, we call Start Cameras, and that takes a device configuration. If we walk through this device configuration, we can see what we're doing. We're setting our color format to be color BGRA 32. So we're asking the color camera to output 32-bit pixels with BGRA information inside of them. We're setting our color resolution to be 1080p. And we're setting our depth mode to be narrow field of view 2x2 bend. And we'll get into what that means in a little more detail in a little bit. We're also setting synchronized images only equal to true. And what this does is when frame data comes in from the camera, sometimes there can be either CPU contention or USB contention, which causes not all of the frames to come in. So synchronized images only equals true means that if, for example, the USB layer had to drop a color image, the SDK will go ahead and drop the corresponding depth image for you. So you don't have to handle situations in which you get only one type or the other. And then we have to capture a couple of other pieces of information. We need to cache our color width and color height as member variables. And to acquire these, we ask for the calibration of the device, we ask for the color camera calibration, and then we ask for the resolution width and the resolution height, respectively. We feed those into our writable bitmap so that the writable bitmap has the same resolution as the color image on our camera. All right, so that's our first set of code. So let's fire this up, see what happens. All right, so our app is pretty boring because we haven't actually taken any images off the camera, but if you look at the camera here, you can see that there's a white light on the front, so we've successfully opened it up. All right, so let's map some Kinect for Windows concepts over to Azure Kinect Sensor SDK concepts. So a Kinect sensor in Kinect for Windows is called a device in the Azure Kinect Sensor SDK. Kinect sensor.open is device.startCameras. And the frame description, which was used to get metadata about resolutions on the frames for Kinect for Windows, that information can now be found in the calibration store on the Azure Kinect Sensor SDK. All right, so when we did Start Cameras and we configured the device, you saw that we picked some options. We picked some color pixel formats, we picked some resolutions, and other modes for the camera. So let's think about a few things that are important when we're configuring our camera. First of all, there are native pixel formats that come out of the RGB camera on the device. Those are MJPEG, NV12, and YUY2, depending on the resolution. And those will have the best performance because we don't have to do any processing on those once they come off the camera. In our application, we selected BGRA 32. Inside of the SDK, we're doing a conversion from these native pixel formats to BGRA 32, which we'll be using in our app. But if your application can use one of the native pixel formats, you should get better performance out of that. You'll notice I didn't specify any frame rates when we set up our camera. So that means that we're using the default frame rates and the maximum frame rates of 30 frames per second for both depth and color. You can independently change those, but to 15 or 5 as well. But for synchronized images, you'll want to select the same on both cameras. And then the depth mode. So you saw that we selected narrow field of view 2x2 bend. When we're talking about depth modes, there's trade-off between field of view and also binning versus unbinning. It's important to remember that bend modes mean less jitter and more range. They sacrifice some resolution in order to do that. And then also when we're configuring our device, we should think about the camera overlap between RGB and depth if we want to use those together. So let's drill into that a little bit more. Here's a scene that I captured in our hallway in our office. So on the left, you can see the color image of what that scene looks like. And on the right, I have 4 images in a grid that show you the different depth modes of the camera. On the left side, you'll see the narrow field of view images. In there, we have both the bend and unbend narrow field of view. So you notice it has the hexagonal shape if you're in this narrow field of view. By narrow field of view, we mean that we're taking the light from the camera and we're putting it into the IR light that we emit to do depth sensing, and we're putting it into a smaller space so that we get more range, but we sacrifice the field of view of the camera. So you'll notice, for example, in the narrow field of view imageries, I don't see the door on the right in the depth images that you can see in the wide field of view. If you compare the narrow field of view binned to the unbinned and look at the ceiling in the kind of green section, you'll notice that I get more of that ceiling recovered with the binned mode than I do in the unbinned mode. In the wide field of view side, you'll notice that I'm seeing more, right? I'm seeing more of the floor and more of the walls and ceilings on the top and bottom. And then you have the same trade-off between binned and unbinned. If you look at the ceiling again, you'll notice that I can see further. I can see things that are further away with the binned mode than with the unbinned mode. So when selecting a depth mode, the important things to think about are how much range do I need, how big of a space do I need, and how many pixels do I really need per object for my application. Also, when considering those and combining them with color camera, it's important to consider how much there is overlap between the cameras. So here's some pictures that I've taken from our documentation that will be posted when the camera goes on sale. And you'll see that we have different fields of view for our different cameras, and these diagrams show you how they overlap. So for example, on the left side of this, we can see that the RGB camera in 16:9 mode does not quite cover the entire narrow field of view depth, but in 4:3 it does. So if you want full overlap in the narrow field of view, you'll want to use the 4:3 color modes. And then we have similar pictures from the tops and sides. If you are using a K4W application and coming to Azure Kinect, the most similar resolution for RGB would be 1080p, and the most similar depth mode would be our narrow field of view unbinned. All right, so there's some information about how to configure your device once you have one. Let's talk about how to actually get the images, the captures, off of the device. All right, so let's go back over to Visual Studio. Oops. All right, so if we go down now to our main, or our window loaded method, you'll notice that we're going to create a while loop here. And this is a while loop to go get imagery from the data, imagery from the camera. And we have this using statement, and we're using an Azure Kinect capture. A capture has a set of images inside of it, and that capture is going to come from an asynchronous task that we start up. And in that task, we are going to say this.connect.getCapture. So getCapture is a synchronous call on the Kinect device in order to go get a capture from the camera, and we're using task.run to make that asynchronous. We have a using statement because the capture has all the memory associated with the images that come from the camera, and they're disposable. So we want to make sure we dispose of those when we're done with them. And then for now, we're going to go and just take the capture.depth.timestamp and put it out to our status text window. So let's fire that up. All right, so we're still not displaying anything. It's not very pretty, but it's a little more exciting than it was before. We have the white light, like before, and you can also see that we have a counter counting up, right? So this is our timestamps coming in off the depth camera. All right, so let's talk a bit about what we did there, and then we'll get to displaying some actual pixels to the screen. So when we get a capture off of the Kinect, that's most synonymous to what was called a multi-source frame in the Kinect for Windows API. There's no longer a frame arrived event as an asynchronous event. There's the get capture, which is a synchronous method. And then we no longer have the notions of a color frame reference, acquire frame, and depth frame reference, acquire frame. Those have been replaced with just .color and .depth off of the capture object. So what is a capture? I keep using this word, so let's drill in a little more to what that means. A capture is a container for multiple related images. In the Azure Kinect Sensor SDK, the most common reason that images would be related to one another is because they're time synchronized, right? So they came from the color camera and the depth camera at the same time. In the C API, a capture is a reference counted type and a disposable type in C#. Similarly, for the images it contains. So a capture can contain up to the depth image, the infrared image, and the color image. So the depth image and the infrared image both come from the same camera, and the color image comes from the color camera. When we think about the types that are associated with these, the depth image contains unsigned 16-bit integers that represent the z distance from the camera in millimeters, and the infrared image represents the amount of illumination returned by the camera's emitters and bouncing off the scene and back into the camera. And the color image is standard color information. All right, so we've opened the device, we've acquired the captures. We're going to skip down in this workflow, and we're going to actually draw something out to the screen. Coming back over to Visual Studio, we have our writable bitmap. We're going to lock the writable bitmap, which allows us to go change its pixels. We're going to grab the color image from our capture. We're going to specify a rectangle that is the full size of the color image, because we're going to be replacing all of the pixels. And then inside of an unsafe block, because we're accessing the raw underlying pixel data, we're going to say this.bitmap write pixels. We're going to give it the underlying buffer of our color image. And then we also need to give it the size of the color image and the stride of the color image. And you notice those are properties of the image object, the color image object. Once we're done with that, we'll add a dirty rect to our bitmap, and we'll unlock the bitmap so that it can be presented to the screen. All right, so there you are, on an Azure Kinect. All right, so let's talk about some conversions again. The underlying buffer property in Kinect for Windows is just the buffer in the Azure Kinect Sensor SDK. And there was a notion of locking an image buffer in Kinect for Windows, which is roughly synonymous to a reference method in the Azure Kinect Sensor SDK. The only difference is that if you're currently holding on to the capture or image object, or an image object you got from the capture, there's not a need to call reference unless you're passing that off to another thread. Reference just creates an additional native reference to give into the managed layer in order to keep the dispose on one image call from disposing the memory under all of them. So if you're doing multi-threading, use reference, or you have multiple algorithms processing the same image, use reference. Otherwise, you probably don't need to. All right, so we've opened our device, acquired the captures, drawn some pixels out to the screen. Let's start to get into the more meat of it here. Let's figure out how to deal with the depth camera imagery and get that into the perspective of the color camera. All right, so we have two cameras on the device, and they both have their own coordinate systems associated with them. The color camera is on the outside of the device, and the depth camera is more towards the middle. They both have the same coordinate conventions of x to the right, z forward, and y down. You'll notice, though, that the depth camera is slightly tilted from the color camera. So it's important that you use conversion methods in between the two cameras and don't just try to directly use pixel coordinates in one or 3D coordinates in one and map them to the other. In order to do that, we provided a set of APIs to allow this to happen. These allow you to map from depth camera 3D space, color camera 3D space, depth camera 2D pixel space, and color camera 2D pixel space. So we provided conversion methods between all those different ones. This will be posted online, so you'll be able to read all those there. There's a couple of important notes on those methods. First, the calibration functions, the ones with calibration in their name, are designed to operate on single points. They're unoptimized code. This is up in our open source SDK, so people can see how things work, potentially integrate those algorithms into your own design of how to do calibration or transformation operations. And then so they're recommended for operation on single points. So if you have a single 3D point and you want to figure out where that is in a 2D pixel space, use the calibration functions. If you want to do whole image operations, you want to take your color image and convert it to your depth camera perspective, or your depth image and convert it to your color camera perspective, it's important to use the transformation functions that operate on whole images and are GPU accelerated. We've also changed some of the conventions in Azure Kinect from Kinect for Windows. We're now the same as OpenCV, so OpenCV interop will be easier for those of you doing that. This means a couple of things. One, 0, 0 is the center of the upper left pixel in 2D. In Kinect for Windows, it would have been 0.5, 0.5. Units are in millimeters, and then as I talked about in the previous slide, y now points down and x to the right instead of y pointing up and x to the left. All right, so let's talk about our transformation functions in a little bit more detail. Here you have a representative image of both our color and our depth camera of a scene captured in one of our teammates' offices. So let's talk about what it means to take the color camera and convert it into or color image and convert it into the perspective of the depth camera. So when we perform that operation, we've warped the image, and we now have a color value for every single depth pixel. There's some depth pixels that we have for which the color camera did not observe that part of the scene because they're not located in the same place. So the color camera can't see behind some things that the depth camera can. So that causes this doubling effect when you use these operations at the left edges of items. This is just something to be aware of. This is an artifact of the kind of fast implementation that we have for doing this operation. There are ways to get rid of this artifact, but they're more computationally expensive. And we provide the code for how this works, so if you want to implement those other versions, that's possible as well. Similarly, when we convert the depth image into the color camera perspective, you get shadowing. So you get regions where the depth camera didn't observe something that the color camera did. So you get these invalidated or shadowed out regions where there are no depth values set. So we're going to be using the depth image to color camera in our application. And for a lot of applications, if you're wanting to display something to users, I recommend display like color point clouds or other things combining the depth and color image to users. I recommend using the depth to color operation. All right, so here's some code on a slide. Let's see what that code looks like in Visual Studio. All right, so we're going to instantiate here our Azure Kinect transformation, set that to null, and then we will instantiate it here using this.connect.getCalibration, so we're getting the calibration for our device, and then we're creating a transformation from it. So this means that the transformation is dependent upon the calibration, and the calibration is dependent actually on the configuration of the device. So if you change resolutions, if you change depth modes, or anything else about how the device is operating, you'll need to create a new transformation object, and you'll need to re-inspect the calibration for things like resolutions if you're using those. All right, so we create the transform, then we're going to come down here to our loop. We're going to add an additional using statement. We're going to create an additional Azure Kinect image. In that image, we're going to set the image format to depth 16 because we're going to store transform depth data inside of this image. We're going to have it be the same width and height as the color image because we're converting into the perspective of the color camera. And then the stride of the image, or how many bytes per row, is going to be the width times the size of a uint16. Finally, we're going to come down here and take our transform and call the depth image to color camera operation. We'll pass in that capture object, which has both the depth and color information, and we get out the transformed depth image. Also, just to make this a little more interesting, we're going to draw this out. I've converted the pixel format of the writable bitmap to BRK1001 so that we can see something here, because these are 16-bit pixels instead of 32-bit pixels. All right, so here's our depth imagery from the perspective of the color camera, and there's Erica. Hi, Erica. The wrapping that's going on here are the kind of, you see the values repeating over. That's just an artifact of using that BRK1001. There you guys all are in depth. Yay, wave for the camera. All right, and you'll notice a couple other things about this image. If you look at the edges, they're bowed slightly. Maybe if I point at the floor here, they're bowed slightly, and that's because we've changed out of one lens and into another lens. And also that we've increased the resolution of our depth image because we've converted it into the color space. All right. Let's go back over to our slides. OK, so there was a thing called the coordinate mapper in Kinect for Windows. That's been replaced by the calibration and transformation functions I've just talked about. If you were using something like map color frame to depth space, that's now depth image to color camera. or map depth frame to color space, that's color image to depth camera. All right, so we've opened the device, acquired the captures, done our depth to color operation. Now let's actually segment out our pixels so that we can do that operation we were talking about at the beginning. So this is all becomes our application-specific logic, where we're no longer needing to touch the SDK methods. We're just using the data that they provide. So let's hop in here. We're going to grab a pointer to our color pixels from the writable bitmaps back buffer and a pointer to our depth pixels from our transformed depth buffer. So remember, these are the depth pixels from the perspective of the color camera. Then we're going to loop over all the pixels in the color image, and we're going to perform a check. This check says, is the depth pixel less than 1,000? So is it less than a meter away? And is it not equal to 0? So those black pixels that I was showing in the previous slide where there was the shadowing, those are called invalidated in our documentation. And they have the value 0. So there's a few reasons that a pixel can be invalidated. It can be invalidated because the object is too far away and the camera can't see it because it's too far away. It can be invalidated because the object is dark or darker in IR, so not enough IR light is bouncing off of it for the depth camera to see. And it can also be invalidated because, in our situation, because we've transformed to the perspective of the color camera if it's in that region that the color camera can see and the depth camera cannot. All right, so if it's not invalid and it's less than a meter, we're just going to continue. We're going to leave the color value alone that we copied earlier in our right pixels up here. And then if it's greater away than a meter and we have a depth value for it, then we're going to set it to 0. So this will effectively eliminate the pixel. All right. Uh-oh. Aha, I have a bug. All right, so I forgot to change this back to the color image because we now want to draw the color image instead of the transform depth image. All right, so we don't see anything until Erica gets within a meter of the camera, and there's Erica, and we no longer see any of you. Sad, you all disappeared from the camera. All right, so we've combined our depth and color information, and we've shown you how to perform those different operations. So let's now let's do something a little more interesting. Let's take our Azure Kinect and connect it with Azure. So up on Azure, we have a suite of services called our cognitive services, and those include several different things. For the purpose of Azure Kinect, the ones that I'm super excited about are our speech services, which can be used with the 7 microphone array on the device in order to do things like speaker identification, speech to text, and far field speech recognition. So if you have a case where you want somebody to talk to your device or to understand what people are talking about, the Cognitive Services speech service is a great addition. We also have our vision services, and the vision services do everything from custom vision, where you can provide your own training set and train your own models, to pre-canned models that give you common objects and items in the scene, or are able to caption images automatically. Today, we're going to be using one of those vision algorithms. We're going to be using the one that is able to identify objects in the scene. So what do we have to do in order to add this cognitive service into our Azure Kinect application? So when at the same time we open the device, we're going to initialize our connection up to cognitive services. And then instead of performing the segmentation step that we just added, we're going to be analyzing the images instead. Also, I'm not going to show this step in Visual Studio. I added the NuGet package for the computer vision service into the application. All right, so let's hop back over here. And switch over to another window. All right, so from that NuGet package, I've created our computer vision client and named it Computer Vision. I've also created this bounding rec called bounding box. We'll get to why I added that in just a little bit. And then I created a list of visual feature types. So these are the sorts of things that I want the computer vision service to go off and recognize in my image. Now I've listed a bunch here, like categories, which will tell you the category for the image, description, which will tell you about like a caption for the entire image, faces, the type of image that it is, and tags. But the one that we're actually going to be using in this talk is the objects, the visual feature types objects. Oh, also, if you want to play with cognitive services and the computer vision service in particular, there is a free trial if you've never used it before up on the Azure page. So go check that out online, and you can get some free credits to use with that. All right, so those are the things we're going to be looking for, so let's actually set it up. Here's the computer vision client. We create a new computer vision client. We add in our Azure subscription key to it, and then we tell it which of the data centers we want to go do this processing inside of it. Then we've modified our main loop slightly. So we've said we've added a variable called count, and I increment count every time we go through the loop. And so I'm doing mod 30, so I'm saying, once we've gone through 30 frames, which we're running at 30 frames per second, so every second, we're going to do a few things. First, we're going to create a stream from our bitmap source. So what this is a little helper method that I wrote that takes our bitmap source object, converts it into a JPEG, and in memory into a JPEG in order to stream up to cognitive services. Then we call computer vision analyze image and stream async. And we pass that in the stream we just created, which is that JPEG image of the current scene. We give it that feature list of the features that we want to look for. And then we tell it to continue with the results. So in the continue with, we loop through each of the objects that the analysis found. We look for an item with the object property equal to person. So we're looking for people inside of our image. And then we find the bounding box of that person, and we store it in our bounding box member variable. If there's any exceptions in this process, we catch them and throw them up to that status text window. And then this from current synchronization context is just so that we can do this back on the UI thread. So we did our async operation, and then once we complete the async operation, we'll come back to the UI thread to actually perform this Lambda. All right, so what do we do with that bounding box that we stashed off here? So we found a bounding box for a person. And then what we're going to do is we're going to just, for this application, find the center of that bounding box. So we're going to find the pixel that represents the center point. And then we're going to query our depth map and ask what's the value at that pixel location. And we're going to update our status text with the person is and depth pixels of the person location. So how many millimeters away is that person? All right, so Erica's going to come over here, and we'll get Erica in our camera here. Oh, you guys can't see the status text because it's off the bottom of the screen. And it says, OK, Erica is 1.6 meters away. Now she's only 600 millimeters away. Right? So we've detected her, and we're combining that with the depth information in order to give us context on the scene. So think about if you had a situation where you had a digital sign that you wanted to interact with customers. You could identify the people that are walking up to it. Are they close enough yet to see it? And activate based on that. Amongst many other things. Or say you wanted to detect balls and do something with the trajectory of balls. You could use cognitive services in order to find the balls for you, and then the Azure Kinect in order to tell you where they are. All right, so right now, you guys can go out, and we have a doc up at aka.ms/connectdocs, which describes more information about our camera. You can come visit Erica and I. We'll be down in the booth after this. We're in the showcase section in the, AI? In the AI section, kind of at the back over by HoloLens. So come check us out. We're happy to answer questions and help you understand how to get started. When you get your own device, the devices are on pre-order right now. They'll be shipping in the summer. When you get your own device, come check out our project on GitHub. We'd love you to file issues. Tell us what you want. Tell us what you want us to change. Tell us what's not working. Contribute if you want to give us pull requests. We're taking contributions. We've already had one. And we'd also like you to go off and build amazing applications that delight your customers. And we'll be taking Q&A now if there's any questions. Yes?
How many different types of cameras are you guys actually planning to make? I mean, is it just one with a certain depth, or are there going to be different levels of greater distance or that kind of stuff?
So we have the 4 modes in the one camera right now. We don't currently have plans to produce an additional camera with different specifications on depth ranges.
Yeah, we're looking forward to learning what kind of different modes you guys are looking to create with your different applications, and then we'll be tailoring our roadmap accordingly.
You have to actually do an intrinsic calibration for every one of those modes and save it off?
So we have the calibration for all those modes inside the device. And when you call that .git calibration method, it gives you the calibration for the mode you've currently configured it in. So you would only need to save them off if you want to use different modes and then do post-processing later, maybe. But we also have a recording API that will save the calibration information along with the recording and then give that back to you when you play it back. So there shouldn't be a need to go stash them all. Yes?
How many of these cameras have you connected together? What kind of cool things have you?
So I think we have done 4 or 5 in order to capture a space and stitch together a point cloud of a person moving about that space. There's not a physical limit to the number that can be connected together. There will be some practical limits of if they're all pointing at the same space, eventually they'll all be emitting IR light and you won't be able to spread them out enough to avoid interference with each other. Yep.
With the data that you've able to capture, have you been able to feed it into HoloLens 2 to be able to kind of give that?
Sure. So the question is, have we fed data into the HoloLens 2 from an Azure Kinect? That's something we're interested in exploring. We haven't actually built that experiment yet. There was a question over here.
Oh, I may have missed it, sorry, but I was wondering what are the most exciting use cases or amazing applications that are envisioning to make use of?
Sure. We talked about a few of them earlier, but you can think of things like in manufacturing, being able to understand workers, being able to understand the 3D environment, how things are moving around in the space, how people are moving around. There's a bunch of applications in healthcare. As well. Yes, we're definitely more on the industry applications with this product itself, less on the gaming side of things like we were in the past. Sure.
Go for it.
Where are you guys right now in the development cycle? Is the engineering done, or are you just trying to get it through production? You said it's going to be available this summer.
We are pre-ordering devices right now, and the devices will start shipping this summer.
So the engineering's done.
This is the camera you'll get.
That one specifically?
Yeah, everybody gets the same one. You have to share. Yes?
What about different countries? You say Europe, for example?
Go ahead.
Yeah, we are currently shipping in US and China. We plan to announce future markets later this year.
So in the situation where you have multiple cameras, are you guys going to be getting rid of the duplicate data, or are you expecting us to parse through it?
So the question was, are we going to be getting rid of duplicate data with multiple cameras? We don't currently provide any specific API functionality for dealing with multiple cameras other than the ability to open them and get the streams from all of them. But if there's if there's overlap and there's desire to solve some of these problems, it's definitely something we're interested in exploring. So give us feedback, tell us what you want. Yes? So the maximum resolution of the depth camera is 1024 by 1024. If you're operating that full megapixel mode, you only get 15 frames per second. The wide field of view is 512 by 512. And then the you're going to stretch my knowledge here. It's like the narrow field of view. If you go to that Kinect docs, it has the exact specification up there. I don't want to say it and be wrong.
I think, were you asking what the accuracy of the actual depth
Oh,
was?
sorry. So accuracy of depth is dependent on a few things. One, how far away the object is, and two, the IR reflectivity. So it'll be better the closer you are and the brighter the object is in IR. Overall, the jitter characteristics should be better than Kinect for Xbox One. I'll do one from over here.
So I saw during the mixed reality dev days that in the lab you guys had a Kinect recorder. Is that similar to the existing Kinect recorder where you can record screens and play it back through your app? And question number two is, if that is the case, can you guys post maybe a generic string of records or a generic record of screens so that we can start building before we have the device?
Yeah, so first question is there a recorder? Can you play that back? So yes, there is a recorder, and you can play it back. It's a little bit different than the Kinect for Windows recorder in that one used a custom container format. We're now using MKV or Matroska as our container format. So you can use standard tools like FFmpeg in order to interact with it. For the second question, which is can we post a stream online for people to play with, we will consider that and work on getting
It's something we're looking into right now.
Yes?
Will this UWP app run on Xbox, especially also the body tracker?
So the question was, will UWP run on the Xbox? The device does not support Xbox.
We have this great service for basically hooking up things in special regions, right? So we have this special service for Kinect. Is there any integration between Kinect for Azure and that? That's question one. And question two is, when we look at the cognitive vision services, right now you're only using the RGB data. Are there some plans to actually use the depth data there as well?
Yeah, so the first question was about the spatial service. Are you talking about the Kinect service?
I'm talking about the spatial anchoring service.
Spatial anchor service, yes. Okay, so both these questions are awesome. I love them. You're thinking in the right direction. Please give us feedback. Tell us that you want these things, and we'll see what we can do. Let's see, I haven't done one from back here.
Yeah, can you tell me about the body tracking SDK for this Kinect and if skeleton data is still available offline?
Yeah, so skeleton data will be available offline, and the body tracking SDK is a separate SDK, so it's a separate download. But other than that, it provides you basically the same information that you got with Kinect for Windows, and we're hoping at a much higher quality than you got with Kinect for Windows.
And if you want to see that one working in action, come by our booth either today or tomorrow, and that's where we have it up and running.
Is there a use case with some of those online already?
So our documentation is not live yet. It will go live when the devices actually start shipping. There is this document which gives you more information about the device. Yes.
Skeleton data from multiple cameras, are they going to be mapped to the same person? Like one skeleton on one camera is going to be mapped to the same person on the other camera, maybe?
I don't know.
No?
So the base ability to tie those cameras together and then extract those streams will be available as part of the sensor SDK initially. We are looking into ways of potentially calibrating cameras and providing that information from multiple cameras, but that won't be part of what initially launches this summer. I think this over there.
Yes. In regards to IoT Edge, is this device considered IoT Edge-like device? And if so, could we push modules down from IoT down into, from Azure IoT down into the Kinect to run?
Yeah, so the device itself is USB-C connected, so it can be paired with multiple different machines. We do have people in our office who've taken it and put a Nuke or other small form factor device with it, and then provisioned it as an IoT Edge device and push containers containing the SDK down in order to run applications on it.
And sample code will be available for that as well when we launch.
Yes?
I know you addressed earlier that there isn't any current support for Xbox, but is there any plans for a UWP SDK to be released
So the question was, will UWP SDK be released? There are currently no plans for UWP SDK. If there's something we get a lot of feedback for, we would consider adding it. So the question is, does the device have any sort of plane detection capability like HoloLens does? No, that's not in our SDKs today. But given that we run similar things on HoloLens, it may be possible in the future. In the back. So the body tracking that we'll be shipping originally ends at the wrists. The question was, does body tracking have hand tracking? Sorry. Well, ends at the wrists. And we will, we are also using the same camera for running the hand tracking in the HoloLens, so we're figuring out exactly what our story is there.
You're going to hate me for asking this, but
Never.
would it be possible to sync a HoloLens session, the hands of a HoloLens session, with the body of a Kinect session?
The question is, can you sync the hands of a HoloLens session with the body of a Kinect session? Yes, but you would need to provide a way of putting those into the same coordinate space to start with.
So could we do that with combining the HoloLens with the sensor, with the Kinect?
Today, it would require some of your own wiring, yeah, but it should be theoretically possible.
Just hardware question. Is it completely powered off the USB-C, or does it require a separate power adapter?
So if you're using an A to C converter because of the limitations of the amount of power that can be drawn out of an A port, you'll have to use an additional power adapter. If you're using C to C, so if you have a C port on your machine, then you don't need an additional power adapter.
Any plans for Python wrapper?
That's something we've talked about. We're not currently committed to doing a Python wrapper, but if we have community, either if anybody wants to contribute a Python wrapper and to the open source SDK, we'd love that. Or if there's a lot of feedback, we would consider adding it.
Yes, please.
All right, last question.
Is there any internal memory on the device for storing frames for later use?
There are internal buffers on the device, like if USB gets backed up, but there's no storage in the traditional sense. All right. Thank you all. Thank you for coming.